Hello and welcome. In this video, we're going to take a look at a famous mathematical problem that gives us the rise of integral calculus. Now, what we're going to be taking a look at may seem kind of dull and maybe unapplicable at the moment. We're going to be taking a look at how to find the area under a curve, but above the x-axis. Just an area problem. It doesn't really sound that interesting, but we'll get there. Eventually, this will give us a lot of applications later on. So let's take a look at an example. What we're really looking at here is how do we find the area between some kind of function like y equals f of x and the x-axis. So it's an area bounded by these two lines in this case. I've got the line y equals 1/2 x, and then we've got the horizontal line y equals 0, which represents the x-axis. Now I need to have some sort of boundary here. I could pick an interval such as maybe from 0 to 4. Now that would just give me the area of this triangle. Now areas of triangles are really easy to calculate, just 1/2 base times height. That wouldn't really be a whole new branch of mathematics. We've already figured out how to find the area of a triangle. If I could pick a different interval, I might want to take a look at an interval from something like, 2 up to 6. Okay, well, that's not a triangle anymore, but it's still not a crazy shape here. I've just got essentially a little trapezoid. I know how to find the area of a trapezoid when I have these two parallel sides here. We would just take a look at this sort of sideways, and we could see that we have a base 1 and a base 2, and we could use the formula of 1/2 base 1 plus base 2 times h. It's kind of like finding the area of a rectangle using the average of these two parallel lengths. Again, not really that difficult. We don't need a whole new branch of mathematics at this point in time. But what we're going to get to now is what do we do when the function just isn't a straight line? It's some kind of curve. How do we find, in general, the area bounded above by this blue curve here, y equals f of x, bounded below by the x-axis, and bounded by this interval from a to b? How do we find this shaded area here? Well, that is actually a lot more of a problem, because now we don't have these basic geometric interpretations like triangles and rectangles and trapezoids. We need to come up with a little new way of getting this area. Well, good news is that geometry doesn't completely fail us. What we're going to do is let's try to estimate this area using nice geometric shapes such as rectangles. And then from there, we can get a better estimate and eventually understand what the meaning of this area is as we get closer and closer to an exact value. So let's start off with a really easy shape, rectangles. Well, what we'll do is we'll take this interval from a to b, and we could estimate that it's roughly the area of a rectangle. Okay, well, it's not going to be the greatest estimation. So why don't we use several rectangles? Why don't we take this interval and break it up into smaller chunks? Okay, well, here I've decided to break it up into 4 chunks. This entire area would now be the area of these 4 rectangles added together. But I haven't quite drawn the top of these rectangles yet. I'd have to complete each of these rectangles by figuring out what height to use. They all have the same width. I've just divided up the interval equally into 4 chunks, but I need to figure out height. Okay, well, let's start off with the easy part, the width piece. To find the width of each of these rectangles is a fairly basic calculation. Let's say that the width of each of these rectangles is the same, and it's just delta x. Well, delta x is simply going to be the width of the whole interval divided by how many different little divisions we want. N in this case is 4, but you could make n anything you like, and that will give you the width of each rectangle. Now, to get the height of each rectangle, you would want to take a look at the height of the blue function somewhere in each of those little subintervals. You could choose to use left-hand endpoints. And here's what that would look like. You can see I'm just taking points on the function and then using these 4 left-hand points at the far left edge of every subinterval and figuring out the height of the function and treating them as rectangles with that given height. And that's not bad, although you can see that the area of the 4 rectangles added together is going to be a little bit more than the actual area under this blue curve. I could, in fact, use right-hand endpoints just as easily. And here's what right-hand endpoints would look like. I'm using 4 points on the curve once again, but I'm using the rightmost point on the curve at each of these little subintervals. And it looks like this is going to be a little less area than the actual area I'm looking for under the whole blue curve. Finally, if I wanted to, I could also use midpoints. And here's what midpoints would look like. In this case, I'm picking a point horizontally along the x-axis in the dead center of each of the 4 subintervals. Figuring out what the height of the curve is fairly straightforward. I just plug those into the function, and then I have to use that the height of the 4 rectangles. So in the end, the area is approximately A1 plus A2 plus A3 plus A4. And it looks like this is probably one of my best estimates is when I use midpoints. Now we can turn all of this into a nice computational formula where n can be 4, or it could be as many rectangles as you like. So in general, if you want to find the area bounded by a function y equals f of x and the x-axis on the interval from a to b, we're going to start by dividing the interval into n equal subintervals. So you can just imagine there's going to be lots and lots of these little tick marks, each one being equal width. Now let's take a look at a particular one right here. Let's pick some random interval from 1 up to n, since there are n intervals. We'll call this the ith subinterval. Okay, well we know the width of every interval is the same, no matter which one we pick. Every time we'll need to know the width. And we know how to calculate the width. It's simply b minus a divided by n. Now, for a rectangle, we'll also need to know what the height is. In order to find the height, what we're going to do is we're going to pick a value of x somewhere in that interval. And this is the x-axis, so we'll call this xi. Although, you know what? It's kind of special. We realize here that there are several choices we can use for a point in that subinterval. In fact, there's infinitely many different points in each of these subintervals. We could choose a left, a right, or a midpoint. Heck, we could pick anything we wanted. So we'll call this xi star, and we could develop formulas that make it easy to figure out and calculate all of the left-hand endpoints, right-hand endpoints, or midpoints. Now, to find a height, we need to plug that in and find out what the height is on this function. The height at that particular point is going to be f of xi star. And now that we've got our width and our height, it's pretty easy to calculate area for rectangles. It's simply just width times height. So the area of a rectangle is going to be f of xi star times delta x. Now we have a whole lot of rectangles all using the same area formula. So we're simply going to add them up. And now we'll end up with this really big sum. F of x1 star delta x would be the area of the first rectangle. F of x2 star times delta x will be the area of the second rectangle. And we'll keep adding them up. And you can see here's the area of that ith rectangle, just in general, all the way up to the nth rectangle. Now they all have the exact same width. We can also develop a nice notation that has this ability to add up many things with a repeating pattern like this. We call it sigma notation. Let's see if we can simplify this notation a little bit. We will use capital sigma, sigma being S for sum in Greek here. And well, we know that this pattern is easy to follow. It just goes 1, 2, 3, 4, all the way up to n. So let's say that I is just some generic number that has to start at 1, and it's going to increment 1 at a time until we reach n. And each of the terms of this big sum is going to just be f of xi star for whatever value of I times delta x. And that is going to be our area. Now, total area here is going to be approximately equal to that, since we can never be perfect if we're only using rectangles, and our function is in fact curved. But you can start to see where we're going to go with this. If we bring back some ideas of limits, and then we let n get larger and larger, and we say n goes to infinity, then we should get the area we're looking for. Okay, there's one last piece missing here. We should really have a nice formula for all of these xi star values, so that, you know, it's not just willy-nilly choose anything you want. If you want to use left-hand endpoints, they should be pretty straightforward to get a formula and calculate all of the left-hand endpoints, or we calculate all the right-hand endpoints. They're pretty easy. And in fact, the midpoint is simply just taking the left and right and finding the average. So, quick couple formulas for left and right and midpoints. Let's define the breakpoints of each of the intervals. So let's say xi is a plus I times delta x for I equals 0, 1, 2, 3, all the way up to n. If you have this quick formula, that means that x0 is simply a. That's the farthest left of the entire interval. x1 is a plus delta x, which is exactly the right-hand side of the first subinterval, and it's the left-hand side of the second subinterval. x2 would be a plus two of those extra widths. So now you've gotten the width of two rectangles. You're at the right-hand side of the second rectangle or the left-hand side of the third rectangle. And xn, using the same formula, a plus n times delta x. Well, since delta x is just b minus a over n, that means that xn is equal to b, which is the farthest right endpoint. Now, if we do that, we can define the right-hand rule, the left-hand rule, and the midpoint rule. For the right-hand rule, we say the area is approximately the sum from I equals 1 to n of f of xi star delta x. That's our basic formula, where delta x is b minus a over n. That's always the same. And here we say that xi star is simply equal to xi. So the right-hand endpoints are x1, x2, x3, all the way up to xn. And for the left-hand endpoints, we're going to need to start at x0, which is a, and that's the left-hand endpoint. So the left-hand rule, same exact formula. The only change here is that xi stars is equal to x sub I minus 1. So the first of these values of x you're going to be using is x0, which is a. And the last we're going to be using is xn minus 1. And that's going to be the left-hand endpoint of the nth rectangle. And now finally, we have the midpoint rule. And here we use the exact same formulas. The only difference is that our xi star, the choice of x that we use to find heights of each rectangle, are going to be halfway between left and right-hand endpoints. And you can do that by taking the left and right-hand endpoints and adding them together and dividing by 2 to find the middle. So let's just do a quick example of finding the area under a common function using the three different rules. All right, in this example, let's see if we can approximate the area of the region bounded by the function 4x minus x squared and the x-axis. And we'll use the interval from 1 to 5 using n equals 4 rectangles. And that's just, an example so that we can divide that interval from 1 to 5 up nicely into 4 rectangles. But we could use any n that we want. Now let's try this with right endpoints, left endpoints, and midpoints. The first thing we could do here is, well, it's probably good to label our a and b, and we can calculate our delta x. So in this case, our a is equal to 1, our b is equal to 5, and using our formula for delta x, b minus a over n, we end up with each rectangle having a width of 1. Now, we could also calculate our xi's, and these would be numbered from x0 all the way up to x4, since we have 4 rectangles. So using the formula xi equals a plus I times delta x, x0 is 1, and that's a, and then we add 1 consecutively until we get to x4, which would end up just being 5, which is b. All right, now let's start off with our right endpoints. For right endpoints, we're not going to get the exact area. So instead of saying area equals or area approximately equals, we could just say R4, because this is the right endpoint area when n equals 4. And we're going to be using the formula using sigma notation from I equals 1 to n, summing up f of xi delta x. So that's starting at x1, which is 2, x2, which is 3, x3, which is 4, and x4, which is 5. And we're going to plug those numbers into the functions to find out their heights. So you can see that those points here, our first interval from 1 to 2, we're going to be using a right endpoint. From 2 to 3, our right endpoint. From 3 to 4, our right endpoint. And from 4 to 5, our right endpoint. And you're going to notice that one of these, the very last one here, f of 5 is actually negative. And that's kind of weird. We don't think about areas being a negative value. And that's totally correct. Maybe we should never really think about area being a negative value. But when we are just plugging in heights, we are allowing heights to be negative, and that's going to end up with R4 having some negative values in there. So plug those in. You can see that the height of the first rectangle is 4, and the height of the second rectangle is 3. The height of the third rectangle is 0. And the height of the fourth rectangle is considered as negative 5. And so, since they all have a width of 1, we can take that common width and factor that out, and we just take that width times the sum of all the heights. 4, 3, 0, and negative 5. Multiplying all of those heights by a common width of 1, we end up with the area equaling 2. Seems a bit weird. 2 is a fairly small number for how much area there actually is here, but we're considering both a sum of some negative and positive numbers. Now we can end up with something completely different when we consider left endpoints. With left endpoints, if we have n equals 4, we can say that the area is just L4, which is a good approximation of the actual area. This time around, though, our choice for xi star is xi minus 1, and that's going to be starting at x0, and then x1, x2, x3. And those are the values for x, 1, 2, 3, 4. They are the left-hand endpoints. We need to plug those into the function to find the heights of each of those rectangles, and using the function, we see that the heights are 3, 4, 3, 0. The 4, 3, 0 are the same 3 points that we just used in the right endpoints. But we're using an additional left endpoint when x is equal to 1, and we're not considering the point when x equals 5. This time around, none of these values are negative. We have 4 heights, we add them up, multiply by a common width, and the total area is 10. And neither of these are very good estimates of the actual area under the curve, but we do know that the area should be somewhere between 2 and 10 now. Last but not least, let's try the midpoints. Now, for midpoints, we'll say M4 for midpoint with n equals 4. We're going to take these 5 different points, x0, x1, x2, x3, x4, and we're going to take the middlemost point as our xi star. So between 1 and 2, we have 1.5. Between 2 and 3, we have 2.5, and so on. And these are the values that we're going to plug into our function to find the heights. We still only have 4 rectangles. So plugging these numbers in, I'll just skip a step here. The heights are 3.75, 3.75, 1.75, and negative 2.25. Again, we have a negative height there, and that's going to happen when we have x equals 4.5, giving us some point down here. We've got all of these midpoints now, and we're going to use these to form our rectangles. I'm going to see this is probably a fairly good approximation of the actual area. Using these heights, we multiply by a common width, which is 1, and that gives us an estimation of the area equal to 7. Right now, it's a fairly simple concept. We're really just using a bunch of rectangles. But we're going to get a little more advanced when we start realizing that having n be larger is going to be better, so we'll be taking limits as n goes to infinity. We'll need a little bit more knowledge about how sigma notation works and how we can simplify these sums, and eventually we can get to a place where we can calculate the exact area. But that's going to be for a future video. So thanks for watching, and I'll see you again in the future.